Hello, my name is Tete Kepsi Rashid and welcome to my YouTube channel. Today, we'll be solving some sample questions on algebra which a friend sent to me, specifically on complex numbers and mathematical induction, as well as De-Moivres theory. This will be a very interesting engagement, so please watch the video till the end. So the question he sent was two questions, and one of such questions and the A aspect of it is this. They say briefly outline the principles of mathematical induction. Now, one way of proving mathematical theorems, statements, and formulas is the principles of mathematical induction. And what does it say? The principles of mathematical induction is a technique of proving mathematical statements, theorems, and formulas, which is thought to be true for the basic and every natural number, which is thought to be true for each and every natural number n, because it is true for the basic natural number 1. Or when we are solving certain mathematical statements, formulas, and theorems, we tend to find out whether it is true for the basic natural number, which is 1. When it is true for it, then we can conclude that it will be true for each and every natural number. That's what we say that principles of mathematical induction. It involves 3 cases when we are proving them. Case 1, which is also known as the basic case, we say that n should be equal to 1. That's the basic form. So when n is 1 and is true, we can proceed to go to the second case, which is known as the hypothesis. Then we will say that n should be equal to any natural number, say k. Then in case 3, which is also known as the induction case, we say that n should be equal to a natural number, say k plus 1. Then from here, we prove a mathematical formula, statement, or theory. When the left-hand side is equal to the right-hand side, then we say it is true for all. So this is the first aspect of the question. Now the second aspect is also on proving a certain mathematical statement to be true using the principles of mathematical induction. So the second aspect, or the B aspect of the question 1, says that show by mathematical induction that the sum where n equal to 1 up to where I equal to 1 up to where I equal to n of I square is equal to n bracket n plus 1, 2n plus 1 all over 6. So this is a very common formula that most mathematics students will be familiar with. So when we have sequences, the sum of sequences put together, they form series. That's the sum of a sequence form a series. So we say that this is a series because it's a sum of a sequence put together. So we can say that this is simply, when I equal to 1, we can say it means 1 square plus 2 square plus 3 square plus up to when we have n square is equal to n plus 1, 2n plus 1 all over 6. So this is the series, the sequences that form this series. Now, so if these are sequences that form a series, we can say that the nth term of this sequence is n squared. And the sum of the series, which is xn, is equal to n plus 1, 2n plus 1 all over 6. So now let's find out the basic form, case 1, which is the basic, whether it will be true for it when n equal to 1. So when n equal to 1, we must make sure it means that the sequence, the term of the sequence is equal to the sum of the sequence. That's it. So let's find out. So our 1 square should be equal to, now we substitute when n equal to 1. So it should be equal to 1 plus 1, 2 times 1 plus 1 all over 6. 1 square we know is 1. Should be equal to 1 bracket 1 plus 1 is 2. 2 times 1 is 2 plus 1 will be 3 over 6. So 1 should be equal to 1 times 2 times 3 is 6, divided by 6 will be 1. So we realize that it's true when n is equal to what? Is equal to 1. Then we proceed to the case 2. Then it will be true when n is equal to any natural number, say k. So we let n to be equal to k. So since the case 1 is true, then we go to the case 2. That's we presume that it will be true when n is equal to any natural number, say k. Then we can say our ak is equal to k squared. And our sk will be equal to k plus 1, 2k plus 1 all over 6. Then the case 3, it is also true when n is equal to k plus 1. So what are we having? Our our a k plus 1 will be equal to k plus 1 all square. And our s k plus 1 will be equal to, any place we see n now, we substitute k plus 1 in this. So any place we see n, we substitute k plus 1. So there is n here, we have k plus 1. Another n here, k plus 1, then plus our 1. Then we have 2 into bracket, k plus 1, bracket close, plus 1. All over 6. Now let's polish this very well. Our sk plus 1 will be equal to k plus 1. Then this will give us k plus 2. Then when we open this bracket, we'll get 2k plus 2 plus 1 all over 6. So our sk plus 1 will be equal to k plus 1, k plus 2, 2k plus 3 all over 6. So in sequences, we know that if we have sk plus 1, it should be equal to ak plus 1 plus sk. We know that. So when we substitute this, and the left hand side is equal to the right hand side, then we can conclude this is very true. We know our sk plus 1 to be this. So to be k plus 1, k plus 2, then 2k plus 3 all over 6. So we say k plus 1, k plus 2, 2k plus 3 all over 6 should be equal to our ak plus 1 is k plus 1 all square plus, and our sk is k plus 1, then 2k plus 2k plus 1 all over 6. So this is well simplified. Let's concentrate here. If this side is equal to the other side, then we say it's true for it. So you can say k plus 1, k plus 2, 2k plus 3 all over 6 should be equal to, now the denominator here is 1. So I can say the LCM is 6. So when one go into 1 divides 6 into 6 times this will be 6 bracket k plus 1 square, then plus 6 divided 6 is 1 times this will just be the same thing, k plus 1, then 2k plus 1. Now we can say k plus 1, k plus 2, 2k plus 3 all over 6 should be equal to, now they have a common denominator, so I can bring it out. Now what is common to this and this? K plus 1, so I'll bring it out, k plus 1 out. What will be left? Left with 6 k plus 1 here because we factor one of it out, then plus k bracket 2k plus 1 because this is also factor out. So we have k plus 1, k plus 2, 2k plus 3 all over 6 should be equal to k plus 1 over 6. Then we expand this, we get 6k plus 6. Then this will give us 2k squared plus k. So I want to simplify further. We can say our k plus 1, k plus 2, 2k plus 3 all over 6 should be equal to k plus 1 over 6. Then here, when we arrange, we say 2k squared. Then 6k plus k will give us 7k plus 6. Now this form a quadratic function. We simplify. So when we multiply these 2 by 6, we'll get 12. Factors of 12, on add we get 7, on multiply we get 12. That will be 3 and 4. So we change the linear term of that. I hope you know this by now. So we have k plus 1, k plus 2, 2k plus 3 all over 6 should be equal to k plus 1 over 6, then 2k squared plus 4k plus 3k plus 6. I'll bracket the first two and the last two. So I can say my k plus 1, k plus 2, 2k plus 3 all over 6 should be equal to k plus 1 over 6 bracket. Now what is common here? 2k is common. We bring it out. 2k out. We left with k plus 2. What's common here? 3. We bring it out. K plus 2. So we have k plus 1, k plus 2, 2k plus 3 all over 6 should be equal to k plus 1 over 6. Now I can factor out my k plus 2 out. So k plus 2 out, I'll be left with 2k plus 3. So we can rearrange this very well. So we have k plus 1, k plus 2, 2k plus 3 all over 6 should be equal to k plus 1, k plus 2, then 2k plus 3 all over 6. So you realize that our left hand side is equal to the right hand side. Then you can conclude that it is true that the sum where I equal to 1 up to where I equal to n of I squared is equal to n bracket n plus 1, 2n plus 1 all over 6. I hope you get this. Now we'll go to the C aspect of the question 1, which is also worth 5 marks. This is worth 10 marks. That shows how long it is. So the C aspect of the question 1, which was also worth 5 marks, is in that when do we say a function is a bijection function? So this is on properties of functions. And the function may have 3 main properties. And they are injective, surjective, and bijective function. Now, when do we say that a function is injective? A function is said to be injective if every a distinct element, so we call this domain, and this is the codomain. Now, every distinct element in the domain map to a distinctive element in the codomain. That is 1 to 1. Then we call, when a function is having such a property, we call that function injective function. Now, when two or more elements in the domain map to a distinctive element in the codomain, we call that a surjective function. So this function here is a surjective function. Now, a function becomes bijective. So this is bijective. A function becomes bijective if it is having both the injective and the surjective property. So when do we say function is bijective? A bijective function is a function that is both injective and surjective. So when a function is subjective, we call it an onto function. So we said that when a function is both one-to-one function and an onto function, then it is a bijective function. So a perfect illustration of bijective function is this function here. So you can see that this function is having one-to-one corresponding. That's each and every member in the domain mapped to only and only one member in the codomain, as well as each is also having an onto function, that an onto property. That means each member here mapped to one member, each and every member in the domain mapped to only and only one member in the codomain. So when a function is having such property, we call that function bijective function. I hope I explained to your understanding. We go to the second aspect of the. So we'll go to the second aspect, and for that matter, the last aspect of this our session, where we solve the question 2A and B. Both A and B of the question 2 will have 10 marks. But before we do that, you do subscribe to my YouTube channel yet? If no, please do. It is the only way you can help promote my YouTube channel so that I can record more mathematical content for you. Now let's go. The question says that use De-Moivres theorem to express cos exponent 6 theta in a multiple angle using the fact that z plus 1 over z is equal to 2 cos theta, where z is a complex number and the absolute value of z is equal to 1. So this question is on complex numbers and De-Moivres theorem. Very, very important in mathematics. Now let's establish some facts. So if this is complex numbers and we are applying De-Moivres theorem, if we have z plus 1 over z and is equal to 2 cos theta, so we know that the exponent here is 1 and the exponent here is 1 as well. That's how come 1 is multiplying the theta. So 1 times theta is still theta. Now, if we have z squared plus 1 over z squared, it will be equal to 2 cos 2 theta from De-Moivres theorem. The same vein, if we have z exponent 4 plus 1 over z, please, what will it be equal to? I know you know the answer. It will be 2 cos 4 theta, and in that order. So we are going to use that idea in solving this question. Now, they say we should solve cos exponent 6 theta. However, we know that z plus 1 over z is equal to 2 cos theta. Or in other words, we can say 2 cos theta is equal to z plus 1 over z. Now, how can we get cos exponent 6 theta out of this? It's just a matter of finding the sieve root of both sides. So when we find the sieve root of both sides, we can get cos exponent 6 theta out of this. Now 2 exponent 6. So 2 exponent 6 is 64. So we have 64 cos exponent 6 theta, and it's equal to z plus 1 over z exponent 6. Now how do we expand this? We can expand this using Pascal triangle or binomial expansions. So I'll use Pascal triangle to expand this. Then after that, we substitute and continue from there. So since I want to use Pascal triangle to expand this, I have to establish Pascal triangle coefficients. So with Pascal triangle, I have 1, 1, 1, 1, 1. We add 1 to 1, we get 2. I'll bring my 1, 1 again. I add 1 to 2, I'll get 3. 2 to 1, I'll get 3. So this is 0, exponent 1, exponent 2, exponent 3. So I need exponent 6, so I'll continue up to 6. So 1, 1 again. 1 plus 3 will give me 4. 3 plus 3 will give me 6. And 3 plus 1 will also give me 4. So this is exponent 4. Then we go to exponent 5. 1, 1. 1 plus 4 will give me 5. 4 plus 6, 10. 6 plus 4, 10. 4 plus 1, 5. So this is exponent 5. Then because I need the exponent 6, I have to get a 6. 1 plus 5 will be 6. 5 plus 10 will give me 15. 10 plus 10 will give me 20. 20 plus 5 will give me 15. So I'm going to use these coefficients to expand that. So let me pull it out. Z plus 1 over z exponent 6 using the Pascal triangle coefficient 1, 6, 15, 20, 15, 1. I will say the first one is 1 times z, and the first z will take the exponent here 6. Then 1 over z exponent 0, it will take 0, so it will still be 1. Then plus the next coefficient is 6, so 6z. Now this will reduce by 1, so I'll get 5. Then I'll get 1 over z exponent 1 plus the next coefficient is 15, so 15. I have z exponent 4 now. Then 1 over z square. The next is 20, so 20 z exponent 3. Then 1 over z exponent 3. As this decreases by 1, this increases by 1. So we'll go to the next, and the coefficient is 15. So plus 15. That will be 15 z square now. Then 1 over z exponent 4. The next is 6, so plus 6 z, then 1 over z exponent 5. And the last one, z to be 0, so we'll bring it. So we just have 1 over z exponent 6. I hope you get that. So now we'll solve this error. Get z exponent 6 plus, now this z will reduce one of these z, so we have 6 z exponent 4 there. Then plus, now we have z square here. It will reduce one of these z. It will reduce two of these z. We have 15 z square. Plus, now we have z cube here. It will divide that, so it will be left with only 20. Then plus, now we have z exponent 4 here, and we have z square here. It will reduce this one by 2, so we have 15 1 over z square. Then plus, we have z exponent 5 here. This z will reduce 1, so we have 6 1 over z exponent 4. Then we have 1 over z exponent 6. Now I want to rearrange this. So I have z exponent 6 plus the last one, 1 over z exponent 6 plus 6z exponent 4 plus 6 1 over z exponent 4, then plus 15z square, and plus 15 1 over z square. Then the last one is plus 20. If you do it well, you'll see that it will follow a certain pattern. Now, we can say this z plus 1 over z exponent 6 using Pascal triangle will be z exponent 6 plus 1 over z exponent 6. Then plus 6 is common here. We can bring it out. We have z exponent 4 plus 1 over z exponent 4 in bracket. Then 15 is also common. So 15 out here. Z square plus 1 over z square. Then plus our 20. So since we identified that the expansion of this is this, we substitute this in place of that. Then we'll continue. So, since this is z was said to be a complex angle in the equation, and z plus 1 over z is equal to 2 cos theta, and I've established some fact for you, then we can say that z exponent 6 plus 1 over z exponent 6 will be 2 cos 6 theta. So we can say that 64 cos exponent 6 theta will equal to 2 for this 2 cos 6 theta, then plus 6 bracket. This will be what? 2 cos 4 theta, then plus 15. This will be 2 cos 2 theta, then plus our 20. So now we can expand. So we can say 64 cos exponent 6 theta is equal to 2 cos 6 theta plus, this will give us 12 cos 4 theta plus, this will give us 30 cos 2 theta, then plus 20. Now in the question, they say we should find a multiple angle for cos 6 theta, not 64 cos 6 theta. So what do? We divide both sides by 64. So we can say that our cos 6 theta, cos exponent 6 theta will be equal to 2 over 64 cos 6 theta plus 12 over 64 cos 4 theta plus 30 over 64 cos 2 theta, then plus 20. 20 over 64. We are dividing through. So we can reduce this. Cos 6 theta will be equal to, this will give us 1 over 32 cos 6 theta. I want all of them to have a denominator of 32. So I'll leave this to be 6 over 32 cos 4 theta plus 15 over 32 cos 2 theta, then plus 10 over 32. So since 32 is common to all, I can factor out. So I have cos 6 theta will be equal to 1 over 32 bracket cos 6 theta plus 6 cos 4 theta plus 15 cos 2 theta, then plus 10 as our final answer. So we have found multiple angle formula for cos exponent 6 theta. I hope you get this. So the B aspect of the question 2 for them, which is also of 10 marks, we should find and plot all the root of the cubic root of 1 plus I. And this question is on complex angles. And we are going to employ the knowledge of De-Moivres theory in solving this. So now, from De-Moivres theory, we know that if a complex number is expressed in its polar form, it will look like R bracket cos theta plus I sine theta when a complex number is expressed in its polar form. However, when this complex number is in its polar form is being exponented by another number, we'll have R exponent n from De-Moivres theory. R exponent n cos n theta plus I sine n theta. This you must know by now. However, if the exponent is a fraction, De-Moivres theory is saying that our R bracket cos theta plus I sine theta exponent 1 over n will be equal to R exponent 1 over n cos theta plus 2k pi over n, then plus I sine pi plus 2k pi all over n. Also from De-Moivres theory, where our k is 0, 1, 2, up to when we have n minus 1. This is the fact. So with this knowledge, we'll be able to find the root for the cubic root of 1 plus I. So we can say the cubic root of 1 plus I is equal to 1 plus I exponent 1/3, which is the fact. Now we need to express 1 plus I in its polar form. That's by finding the magnitude and by finding the argument. So R, which is the magnitude, will be equal to the square root of the real part square plus the coefficient of the imaginary part, which is 1 square. So we'll have the square root of 1 plus 1 equal to the square root of 2. So our R is the square root of 2. Now we need to find the argument. You know that the imaginary part, the real part is 1, is positive, and the coefficient of the imaginary part is also positive. It will be found in the first quadrant. So we can say that our tan theta will be equal to the coefficient of the imaginary part over the real part. So tan theta will be equal to 1, and theta will be equal to tan inverse of 1, and the tan inverse of 1 is 45 degrees. So we established the fact that theta is 45 degrees. Our n here is 3. Look at it. So the n is 3. Now how do we get k? Since n is 3, 3 minus 1 will be equal to 2. Remember that. So our k will be equal to 0, 1, and 2. The last one will be 2. So now we know that the roots will be 3. That's when k is 0, when k is 1, and when k is 2. And we know the fact that our n in this case is 3. Our theta is 45 degrees. We just substitute into it to get the 3 roots. After that, we plot, because the question says we should plot. So we have find our R, which is the magnitude, to be root 2. Our argument, theta, to be 45 degrees. We establish the fact that our n in this case is 3. And our k will be 0, 1, and 2. That means we'll have 3 roots for this. So now how do we solve this? We substitute. So we can say that this in its polar form, that's the cubic root of 1 plus I in its polar form will be root 2 cos 45 plus I sine 45 all exponents 1 over 3. Remember, the n is 3. So this will be equal to root 2, which is R exponent 1/3, bracket cos, remember theta is 45. So 45 plus 2k pi over 3, which is n, plus I sine 45 plus 2k pi over 3 from De-Moivres theory. Now we find the roots. So the first one, when k is equal to what? 0. We just substitute k equal to 0 in this, then we get our root. So now the square root of the cubic root of the square root exponent 1/3 will just be 2 exponent 1/6 using indices. Bracket cos 45 plus 2 times 0 K is 0. When K is 0, pi. Remember, pi is 180 degrees in radian, over 3 plus I, the same here, sine 45 plus 2 times 0 pi over 3. Now 2 times 0 times pi will be 0, and 45 divided by 3 will just be 15. We will say that 2 exponent 1 sieve bracket cos 15 plus I sine 15. The same thing applies to that too. Now when we expand this very well, so when we find 2 exponent 1 sieve times cos 15, we get 1.0842. Then 2 exponent 1 6 times I sine 15, we get 0.2905 I to be our first root. So we can say that our first root Z1 is equal to that. We can find the second root. That's when K is equal to 1. So we have the implication that we have 2 exponents. The square root exponent 1/3 bracket cos 45 plus 2 times 1 pi over 3 plus I sine 45 plus 2 times 1 pi over 3. So this will give us 2 exponent 1 sieve. Then this. Remember, pi, this pi is in radians, so it's 180. 180 times 2 will be 360 plus 45 divided by 3 will give us 135. We have cos 135 plus I sine the same thing there, 135. When we expand, so on point 2 exponent 1 sieve times cos 135, we get negative 0.7937. And 2 exponent 1 sieve times I sine 135, we get 0.7937 I. So we can say our second root, Z2, is equal to that. Now we'll find a third root where K is equal to 2. So when K is equal to 2, we'll have the square root exponent 1/3 of 2 bracket cos 45 plus 2 times 2 pi all over 3 plus I sine 45 times 2 times 2 pi all over 3. So we'll get 2 exponent 1 sieve bracket cos, when we do this very well, we'll get 255 plus I sine 255. So I'll point this in the calculator. That's 2 exponent 1 sieve times cos 255. We'll get negative 0.2905. And 2 exponent 1 sieve times sine 255 times the I, we'll get negative 1.0842 I. So we can say this is our third root, Z3. So we know the 3 roots. We can now plot, because the question says we should plot all the roots. So since we find all the 3 roots, the first root is this, the second and the third. We can plot them on a Cartesian plane. So the first one, remember, both the real part and the imaginary part are positive. So it will be fine in this quadrant. So we'll have this, where our theta will be here. We have 1.0842 and then 0.2905. That's the imaginary part on the y-axis, the y-axis, and the real part on the x-axis for the first one. The second one, look at it. The real part is positive, and the imaginary part, or the complex part, is in negative. So it will be found in this quadrant. The real part is in negative, and the imaginary part is in positive. It will be found in this quadrant. Thus, x is negative, and the y is positive. So I have something like this. So I have 0.7937. It's already in the negative, so there is no need to write negative here. Then we have 0.7937 for the imaginary. Then the last one, look at it. Both the real and the imaginary part are in negative. So it will be found in this quadrant. So we have something like this. We have our theta here. Remember, the real part will be 0.2905 in negative, and the imaginary part will be 1.0842 in negative. So we have plotted all the roots on our Cartesian plane. Oh. Sure. So end it here today. I will indulge you to share my videos, comment, because your comment keeps me going. Then subscribe to my YouTube channel. This will make my YouTube channel grow more, and I can record more mathematical content with you. Until we meet again, my name is De-Moivres Theorem and Proof.